everyone. Thanks for being here. I appreciate that very much. Like Glita presented, I'm Yarden. I'm here to talk about some new attack surfaces and defense surfaces on Windows. Most of what I do is Windows, so apologies to the non-Windows people who might be in the audience. So I'll introduce myself first. I'm Yarden. I've done mostly Windows work for most of my career. I've worked on EDRs. I've done consulting and project work. Mostly did defense work, but also some offensive projects, exploit development, a lot of research into exploit mitigations and exploitation techniques and bypasses on Windows. Before and a little bit during my InfoSec career, I was a circus artist. No longer am, just a hobby. At some point in the distant past, I was also a pastry chef and a bunch of other things. So after the talk, feel free to come and ask me about any of those if you're interested. So this talk, the original title was Forensics in the Age of Exploits. It changed to Security in the Age of Exploits when it became a little bit more of a general security talk. So the classic Windows exploit, and of course that is very high level, had a few steps. You need to make it to the machine through some vulnerability or phishing or getting someone to download a binary that they shouldn't and run it. There's a million ways. Once you're on the machine, assuming you're not already running as a very privileged process, you might need to elevate yourself to a more privileged process. You can do that directly, you can do that through the kernel, you can do that in lots of different ways. And sometimes your entire goal is to make it to the kernel, to install a rootkit or a bootkit, to gain some persistence on the machine. So the main attack surfaces would be from a less privileged process to a more privileged process, and from a more privileged process to the kernel. Not talking about hardware and firmware in this talk, because they're a little bit out of scope. In modern Windows systems, that changes and becomes a little bit more complicated. So originally, we only had these few things. Attackers needed to know how to get to the machine. Attackers needed to know how to elevate themselves. And if they needed to get to kernel, attackers needed to know how to get to the kernel. There's, of course, a lot of different options in each one. But a few examples of each category. The initial access can be through a browser exploit. It can be through a flash vulnerability, through Office or some PDF parser or an image parser. It can be some kind of network vulnerability. In a lot of those cases, you end up in a relatively unprivileged process like a browser or Office or Adobe Reader or WordPad or any of those. From there, you need to break out to a more privileged process. You can do that by exploiting some redirection path or some DLL hijacking, dropping a DLL in a place where a more privileged process will load it, or redirect a more privileged process through a junction, a redirection point, a symbolic link, to either load a DLL or use some resource that you can use to inject code into it, or sometimes just direct code injection. If you need to make it to the kernel as your final goal or as a path to elevating yourself to a more privileged process, there's system call vulnerabilities. There's vulnerabilities in third-party drivers through Yoctl interfaces. There's plenty of vulnerabilities in Win32k. Those are some common options. The most common thing kernel vulnerabilities are used for is usually to steal the system token or the token of a more privileged process to give it to your own process or to a child process. Then Microsoft went and made things complicated. They added a lot of different layers of security. They took some processes and made them even less privileged through sandboxing with app containers and server silos and app silos. They took some processes and made them more protected through protected processes and protected process light. They also added a hypervisor. Now with the hypervisor, your system is not really your system anymore. It's a VM. What you think of as your host is actually a VM, and there is a second little VM running alongside it for the really, really protected processes in Windows. That's the secure environment, or VTL1. That's where Microsoft now puts your credentials. They're no longer in LSASS, they're in a different process in VTL1. That's where they keep all sorts of security configuration, code integrity configurations, and things like that. So now even making it to kernel mode doesn't necessarily give you full access and ownership of the machine. If you're using Credential Guard that stores your credentials in the secure process in VTL1, even having a kernel driver doesn't give you access to your credentials, and some things are protected by the hypervisor itself or any VTL1 mechanisms. So now actually owning the machine means you need to go through a whole lot more steps. If your initial access is through a browser, that browser is now likely sandboxed. You will have to break out of the sandbox to run in a regular process. From there, you would need to elevate yourself to a more privileged process or to the kernel. And now even the kernel doesn't give you everything you need because some things are protected by the hypervisor or the secure environment. Now, I won't talk about all these different mechanisms and all these different attack surfaces today. A lot of people spoke about many of these. But just to map out some new attack surfaces, breaking out of a sandbox, elevating to a regular process, and then accessing a protected process or a PPL. For example, EDRs nowadays mostly run as protected process light. So if it's part of your malware or exploit, you need to disable the EDR product, you will need to find a way to inject code or terminate a PPL, which is also not all that easy. You can get to the kernel through different exploits, but from there, if you want to really own the machine, you would need to compromise the hypervisor, which in Windows is Hyper-V. Or you can get from the kernel to the secure kernel that manages the secure environment, VTL1. In the secure environment, there's also user mode processes called secure processes that you can only interact with if you're already in VTL1. And regular processes can also host enclaves, which will be the focus of this talk. So in diagram form, this is a diagram that I actually stole with permission from Microsoft and recolored and redesigned a little bit. That's the current rough security model in Windows. Microsoft actually just announced VTL2 after I already made these slides, but that's not relevant for this talk anyway, so let's assume this is still all there is. VTL0, or the normal mode, normal world, is what people think of as their host. That's where all your processes are. That's where your kernel is. That's where your browser and PDF reader and kernel drivers all live. VTL1 is the secure environment run by Microsoft, and you can only run there if you have a special signature called isolated user mode signature that only Microsoft has, and Microsoft only applies to some very, very specific processes and drivers. So even 99% of Microsoft code can't run in VTL1. That's where your credentials are right now. That's where your VM management processes run. That's where the kernel CFG bitmap is, and code integrity policies, and all those things you would want to compromise as an attacker. Now, VTL0 is the same as it always was. You can reach it, you can elevate yourself, you can load a kernel driver if you manage to do that. But if you want to get to the really valuable things in the machine, you would need to get to VTL1 either by compromising the secure kernel, or compromising the hypervisor, or finding a way to compromise any of the secure processes. So, a little bit more detail on the new attack surfaces. You can get from kernel to Hyper-V by finding a vulnerability in any of the Hyper-V resources. To talk to Hyper-V, there is a mechanism similar to system calls called hypercalls. If you find a vulnerability in that, that can compromise Hyper-V. There is also the VM bus that manages the devices on guest machines that has also had bugs in the past. You can get from the kernel to the secure kernel through another mechanism similar to system calls. That's called secure calls. So when the kernel needs to ask the secure kernel to do something, to start a secure process or thread, to load a secure module, to query any policies, it does that through secure calls. There is about 150 of them right now that operate kind of similar to system calls, and vulnerabilities in those can also potentially compromise the secure kernel. And there is also a reverse mechanism. Because the secure kernel can't really do everything on its own, it doesn't have a full memory manager or scheduler, for example, it needs to ask the normal kernel for a lot of things. That's called normal calls, and if the kernel lies or tries to compromise the secure kernel through the replies, for example, giving it invalid memory or giving it addresses that aren't where the secure kernel thinks they are, that could also be a vulnerability. There is also a mechanism to communicate from normal processes to secure processes. Secure processes, going back here for a second, secure processes living in VTL1 are very limited. VTL1 is not really a full Windows environment. It doesn't have any access to hardware, to the file system or registry or network stack or any of that. So to access the machine in any way, they need to go back to VTL0. So they need to communicate with normal processes. They do that over RPC. So there is RPC in the secure environment, and some VTL1 processes do use it. And there's enclaves. Enclaves are even more limited than secure processes. They don't have access to RPC, for example, but they are hosted by a normal process. So the normal process can interact with its enclave through something called secure calls. They're also kind of like a system calls into the enclave. And enclave calls go both ways. The process can talk to the enclave through enclave calls, and the enclave can call functions back in the normal process through an enclave call as well. Now, if you manage to compromise an enclave or a secure process, that gives you, back here again, that gives you another interface into the secure kernel. From a VTL0 regular process, you have no direct interface to a secure kernel. You have to either go through the normal kernel by compromising the kernel or loading a driver, or if you manage to compromise a user mode process or enclave in VTL1, then you can talk to a secure kernel through the system call mechanism. So this talk will focus on enclaves, mostly because they're a relatively new mechanism, and the newest part of them is that now they're available to third parties. Enclaves were not super interesting until pretty recently, because enclaves as a target on their own are not the most useful target. Mentioned that VTL1 is a much more limited environment than VTL0. It is limited in a lot of ways. There's no access to hardware or any of the device stacks. There's also not as many system calls and operations as you're used to. There's no open process, for example. Enclaves can't access any other enclave or any secure process. Secure processes can't access each other's memories directly. Overall, there's about 50-something system calls available in VTL1 compared to almost 500 in VTL0. So compromising a secure process or an enclave doesn't automatically give you anything related to any other secure processes or enclaves. Also, until recently, there were very, very few enclaves in the machine. Microsoft used enclaves for one or two things, like SGRM that has since been disabled. So unless your target was that very specific enclave, targeting enclaves really wasn't a super interesting thing to do. Now Microsoft allows third-party enclaves. So now to run in the secure environment, you need one of two signatures. either the isolated user mode one that is still only for very specific Windows code, or the Enclave EKU that Microsoft makes available through Azure Attestation Signing. So if you use that, you can sign a DLL and then load it inside of an enclave. That on its own still doesn't give you necessarily everything you want. An enclave is a very limited way to run things. So enclaves were first created by Intel for SGX enclaves, and then adopted by Microsoft as VBS enclaves. And essentially, enclaves are a way to run code in a secure way, but in a way that is separated from the rest of the machine in both directions. Enclaves have to be predefined. So you can have a main DLL as an enclave. It has its dependencies that also have to be signed according to the VTL1 requirements. And you have to predefine how many threads will be assigned to the enclave, how much heap memory. All memory in the enclave that is executable has to be signed with the right EKU. There is no virtual protect. There is no create thread. There is no virtual alloc, so you can't allocate any more memory or create additional threads. You can't load any other DLLs. You can't have any dynamic or unsigned memory. So even if you compromise an enclave, you are still relatively limited. So why target enclaves at all? Well, first of all, maybe the enclave itself has something you want. Right now, Microsoft uses enclaves for two main things. They use it for the Edge wallet, where they store passwords, and if you have Edge save your credit card details, for example, all of that is saved encrypted in an enclave. The other thing they use an enclave for is the new recall. After Microsoft designed the original recall that takes screenshots and key logs and saves everything you do on the machine, the security industry didn't really like that very much, especially with their original design not really being as secure as they claimed it was. So they took it all back, redesigned it, and by redesign I mostly mean put it inside of an enclave, and now it's secure. Well, mostly secure. It is much more secure than it used to be. You can't just go and open the database like you could in the previous design. But I'll show how putting it in an enclave doesn't necessarily mean it is entirely secure. But if the enclave itself is not what you're after, compromising an enclave still can be valuable because that gives you another surface to the secure kernel. So if you find any vulnerability in any secure kernel system call, unless you're running VTL1, you can't call it at all. But compromising an enclave or a secure process gives you that interface that you might need. So it's not necessarily the goal, but it is a step towards a potential goal. So how do you even target an enclave? The only way to communicate with enclaves is with a call enclave API. It's an API that takes a pointer to a function inside the enclave, takes a pointer that is a parameter, and sends it to the enclave. So all exported enclave APIs receive one argument that is a pointer to whatever structure they want it to be. Of course, you only need to compromise an enclave if you can't create and sign one of your own, which is, of course, not an option because no one has ever received a code signature from Microsoft that wasn't supposed to. So you will need to target an existing enclave in that scenario. So with enclave calls, you can call any API in the enclave. You can find functions in enclaves with getproc address, so the loader knows how to manage enclaves and how to look through enclaves for APIs, and then you can call it with call enclave, send a parameter pointing to whatever data the enclave expects to receive, or whatever data you want to send. It doesn't have to be what the enclave expects. Because enclaves are more secure and protected environment, they always have to be careful of whoever calls them, meaning the host process. Because the host process should always be assumed to be malicious or compromised. So that attack surface now requires the same type of security that is needed in any privileged component that talks to a less privileged component. So it is the same as system call security. It is the same as RPC or any IPC mechanism security. But Microsoft doesn't really treat it that way yet. Microsoft did publish a developer guide about how to write enclaves without mentioning the word security, even once, with no best practices, with no explanation of the risks and the attack surfaces. So there's potential problems there, especially when third-party developers who might not be super aware of all those risks start developing enclaves. So enclaves can do a few things. Their main goal, at least the one communicated by Microsoft to third-party developers, is to encrypt data. From an enclave, because you are in VTL1, you get special access to a component called the TPM that knows how to encrypt things. So enclaves can seal and unseal data, meaning encrypt it with whatever encryption key they choose and decrypt it with that same decryption key. So for example, what makes recall or the new recall secure is that all your data is encrypted and the encryption key is your authentication information. So to access any of the recall data, you should be required to authenticate through Windows Hello that scans your face. And that should be the encryption and decryption key. That's what is supposed to keep it secure. So what are the risks there? All the same risks you get in a more privileged component. The enclave lives within the memory of the host process and can access the memory of the host process. The only thing that makes it special is that the hypervisor encrypts that memory and makes it non-accessible unless you're running VTL1. So when the host process calls a function in the enclave, it passes in a pointer to an input and output structure. That pointer can be anywhere. If that pointer is within the enclave itself, you could potentially get arbitrary read or arbitrary write. The enclave treats the input or output while it is inside the enclave memory itself. So if you give it an input pointer that is inside the enclave, it will read from it and potentially return to you information from within the enclave memory. And if you give it an output pointer that is inside the enclave, it will write to it, and you can potentially get an arbitrary write. Microsoft doesn't give you a function to check if an address is within the enclave. You can do that yourself. Enclaves are supposed to query the enclave limits and implement that check themselves, but in some early enclaves, even Microsoft themselves didn't do it correctly. So expecting that from third-party developers is a bit of a high bar. In other interfaces, like in the kernel, Microsoft does supply functions. If you develop a kernel driver, you have the probe for read and probe for write functions that Microsoft built exactly for that. They didn't build equivalent ones in enclaves. If you give a pointer that is not within the enclave memory, as you should, then that pointer points to memory in the host process, which means if the enclave is accessing that memory, the host process can change it as the enclave is reading it, having double fetch or time of check or time of use or use after free bugs. So all sorts of different problems can happen. So the enclave doesn't just need to verify that the address is outside the enclave memory. It also needs to verify that it's not changing or copy it or capture it to a local variable before operating on it. There can, of course, be logic bugs that are dependent on the enclave itself, in how it operates, how it checks things. Those are a little bit harder to mitigate because those depend on the specific implementation. But even for your basic memory bugs, Microsoft doesn't explain or document that, probably because they haven't felt the need. Unlike kernel bugs, for example, crashing the enclave is not a risk. If you crash the enclave, you crash the process, it doesn't compromise any of the data. So that is not really a risk factor here. And exploiting an enclave only gives you access to the enclave itself. It doesn't give you any direct access to other enclaves or secure processes. What Microsoft didn't exactly take under consideration is that it does give you access to the system call interface of the secure kernel where there can be other bugs. So what is that interface exactly? Well, if you have the choice between compromising an enclave and compromising a secure process, go for the secure process. Secure processes do have a limited surface to a secure kernel, only about 50-something system calls. Enclaves are way more limited and only have access to 20-something system calls. So a lot of things don't even work for enclaves. Enclaves don't have IPC mechanisms. RPC is only available to secure processes, but not enclaves. It doesn't mean there's no bugs, but it can be a little bit more challenging. But enclaves and secure processes both have access to types of system calls that are not available in VTL0, called secure calls. Those are special system calls that have no equivalence in the normal kernel, that do special operations like access the TPM to encrypt and decrypt memory, or do other operations that are only available to something running in VTL1. So if those can be compromised or those can give you any kind of useful information, that can be helpful. So how do enclaves protect themselves? Well, I'll start by focusing on the types of issues talked about so far. First of all, a security mindset. You need to be aware that anyone calling them might be malicious, might have compromised the host process, might be trying to access the encrypted data, or might be trying to exploit a bug in the secure kernel to elevate themselves from that. So never assume anything about the input. Don't assume the address is outside of the enclave. Don't assume that it is not going to change. Don't assume that no one is going to overwrite the data. It would also help if Microsoft documented this and created the appropriate APIs so third-party developers don't have to do that on their own. But until they do, third-party developers should be aware of all those things and protect themselves correctly. Now, those are not the only types of compromise that enclaves can face. For example, enclaves have, the enclave DLL has dependencies. They depend on other DLLs in the system. Those all have to be signed with the right EKUs. But how can the enclave know that the DLL it's loading that is signed correctly is the right DLL and not an imposter or not an older version of that DLL that has known vulnerabilities, or another signed DLL that was renamed to the DLL it expects and has the same exports, but doesn't necessarily do the same things. Microsoft does create an import binding mechanism that is special for enclaves that allows them to bind to very specific dependencies based on a certain set of identities, who the author is, the exact version of the DLL, the exact image hash. So far, it is partially implemented and not used even in all Microsoft enclaves, but the mechanism does exist and will hopefully be improved. But if developers are not aware of it or not using it, or if Microsoft doesn't ship the tools that actually allow binding to all these different identities, that could be a little bit more challenging. When encoding and decoding data, enclaves can also choose to only encode it and to only encode or decode the data if certain things are correct. They can choose to encode the data with the hash of the exact DLL that's encoding it, or the version, or the author, so it can only be decoded by the exact same DLL or author or any other identity. So even if someone else gets access to the encoded data and manages to compromise an enclave or create a malicious one, they still can't decrypt the data. All of those are at this point not really fully complete and not fully working. There's a paper coming that I'm writing together with Alex Ionescu that will publish about all these details and technicalities and some better tools when we can manage to finish it. But it really would be great if Microsoft did publish at least better guidance on the topic. I don't have a clock in front of me, so I don't know how we're doing on time. I can only estimate. But if we're early on time, then we'll get a few minutes off or more time for questions. So in general, I focused on enclaves here, but there's plenty of new attack surfaces in Windows. So you can look at it from multiple directions. You can say, oh, writing exploits is so much harder now. You need to get to the machine and break out of a sandbox and elevate yourself and go to the kernel and go to a secure kernel. And then you can deal with firmware and hardware and all of that. And that is true. You almost never see an exploit chain of one vulnerability anymore. You see ones of 3 and 4 and 5. But there's also much more surfaces to defend. So Microsoft, and that is not just true to Microsoft, that is true for any operating system or any big product, now need to put a lot more effort and knowledge and skills into maintaining all of those and making sure there's no bugs in them. They don't just need to defend the main system call interface, they need to defend the system call interface in the kernel and in the secure kernel and the hypercall interface in the hypervisor and the RPC mechanisms in secure processes. There was just a bug fixed in a secure kernel API that just didn't check an address correctly. So you could pass in a kernel address instead of a user mode address if you were in VTL1 and get an arbitrary overwrite. So it's, a classic bug that you expect to not really see nowadays anymore, but you still see them all the time and showing up in places you wouldn't expect. So there's much more resources and effort need to be put in. So with all those resources being a lot more spread out than they used to be, there might be more bugs showing up or more vulnerabilities appearing. Also, because there's multiple ways to get what you want now, there can be different paths or different interesting exploits coming out of this. Right now, there's no third-party enclaves that I know of. Microsoft only just announced that they only just announced third-party support for enclaves maybe 6 months ago. So it might be a little bit until you see third-party enclaves come out, but when they do, and they might be used by security products or by DRM or by any other third-party company, I do expect to see some vulnerabilities in there and see where that attack surface goes. Thank you, and yeah, I'll be here for questions if you'd like.